Suppose the terms of a sequence can be computed by some formula like where the ai's are all constant. Note that the terms of a sequence Sn depends on the previous k terms, multiplied by constants, but not by each other, and there is no constant term. So we call it a homogeneous, kth order, linear recurrence relation. A suitable ansatz for a homogeneous kth order linear recurrence relation is Sn equals C r to power n. If Sn is C r to power n, then our recurrence relation will be, we'll substitute C r to power n for Sn and all the others. And everything has a factor of c and r to power n minus k, so we can factor that out. And so we get our recurrence relation. And since we don't know r, then we can rewrite this using a variable x to get our characteristic equation. So for example, let's find the characteristic equation for the Fibonacci sequence. Sn is the sum of the two previous terms. We assume Sn is Cr to power n, and so substituting that in we get. And so our characteristic equation is now, an ansatz is justified by whether or not it works. So suppose r is a solution to our characteristic equation, it follows that Sn equals Cr to power n is a solution to our recurrence. Now, to find C, remember that a specific recurrence sequence will have to have initial values. So let's find the closed form expression for the recurrence sequence, where S0 is 5. So assuming Sn is Cr to power n, we'll substitute that in and solve for r. So we obtain r equals 3, so Sn is some constant times 3 to the power n. Now, we know that S0 is 5, so we'll substitute that into our formula, and we find C is equal to 5. And so our closed form expression for this series, 5 times 3 to the power n. Now suppose we take our kth order linear recurrence relation. The characteristic equation will be a polynomial with several roots. So which one do we use? In general, all of them. Suppose r1 and r2 are distinct roots. Then since r1 is a root, we have, and so multiplying everything by c, and this tells us that Sn is in fact the sum of the previous terms. And likewise, c2 r2 to the power n will also solve the general recurrence relation. Consequently, their sum will solve the recurrence relation. And at this point, we can find the coefficients using the initial values. For example, let's find a closed form expression for the terms of the Fibonacci sequence where S0 is 0 and S1 is 1. So our characteristic equation is, which has two solutions, which we'll call alpha and beta for convenience. So a general solution is a linear combination of powers of these roots. To find C1 and C2, we use the initial conditions. S0 equals 0 gives us, while S1 equals 1 gives us, and solving this system of equations gives us, and so we have those two coefficients, and we can use these to calculate the nth term of the Fibonacci sequence.